Text classification is a common NLP task. The problem of classification can be defined as follows. Given a set of records, D, and C is a set of discrete, different labels indexed from 1 till N, and each representing a category. T is our text classification system. We can describe classification task as follows. We need to assign one category, C, to each record X. The problem is usually solved by using a supervised learning approach where a set of training data records and records with known category labels are used to construct a classification model, which would relate features in the underlying record to one of the class labels. And for a given instance, the training model predicts a class label. Text classification is used in many applications, such as newswire service, where classification is required for a large number of documents in real time. Opinion mining, where customer reviews or opinions are often short text documents that can be mined to determine useful information from a review, and typically you can classify reviews into positive or negative sentiment categories. Email classification and spam filtering. It is often desirable to classify email in order to determine the subject or to determine junk email in an automated way. There are different types of text classification. Let's mention two major types that are based on the type of content that make up the document. We have content-based classification. This is a type of classification where priority or weights are given to specific subjects or topic in the text content, and it helps determine the class of the document. For instance, we can conceptualize this example as a book with having more than 30% of content about food preparation. It can be then classified under cooking or recipes. Request-based classification is another type, and it's influenced on user requests, and it's targeted towards specific user groups and audiences. And this type of classification is governed by specific policies and based on user behavior and decisions. To automate text classification, we use several machine learning techniques and concepts, and there are two main types of machine learning technique that are relevant in solving this problem. Supervised machine learning refers to specific machine learning techniques or algorithms that are trained on pre-labeled data samples, also known as training data, and corresponding training labels or classes. This model can then be used to predict the class for future tests once we feed their features into the model. Among supervised machine learning techniques, classification is used for categorical variables, and regression would be used as continued variables. The second approach is unsupervised learning, which refers to specific machine learning techniques that do not require any pre-labeled training data samples, and the focus is more on pattern mining and finding latent substructures in the data rather than predictive analytics. For text classification, there have been a wide variety of techniques developed and designed, and since text may be modeled as quantitative data with frequencies on word attributes, it is possible to use most of the methods for quantitative data directly on text. However, text is a particular kind of data in which the word attributes are sparse, if you recall from our previous lectures, and they're highly dimensional, with low frequency on most of the words, and we do need to account for these characteristics of text. The most common techniques for classification are decision trees, pattern rule-based classifiers, SVM classifiers, and Bayesian classifiers, among others. In decision trees, we use a hierarchical division of the underlying data space, and this hierarchical division of data space is designed in order to create class partitions that are more skewed in terms of their class distribution. And for each given text instance, we would determine a partition that is most likely to belong to and use it for purpose of classification. In a pattern rule-based classifier, we determine the word patterns that are most likely to be related to different classes, and we construct a set of rules. And the left-hand side of the rule will correspond to a word pattern, and the right-hand side will correspond to class label. SVM classifiers attempt to partition data space with the use of linear or nonlinear delineation between different classes. And the key is to determine the optimal boundaries between the different classes, use them for purpose of classification. A Bayesian classifier, we attempt to build a probabilistic classifier based on modeling the underlying word features in different classes. And the idea is then to classify text based on the posterior probability of documents belonging to different classes. In terms of features, we cover already traditional and advanced features representation in the last lectures that can be used in the text classification tasks. Let's briefly look at multinomial naive Bayes classifier that will be used in today's example. This is a special case of popular naive Bayes algorithm used specifically for prediction and classification tasks where we have more than just two classes. Naive Bayes algorithm is a supervised learning algorithm that uses the popular Bayes theorem. Given the response class variable y and a set of n features in the form of a feature vector x1, x2, xn, and using the Bayes theorem, we can denote the probability of occurrence of y given the feature as following this formula. And recall this formula can be interpreted as posterior equal prior multiplied by likelihood divided by evidence. And we can look at the example with specific words. Probability of sports given a string of a very close game would be equal to probability of a very close game given sports multiplied by probability of sports and divided by probability of the string a very close game. Now we need to remember our assumption is that the probability of occurrence of different terms are independent of one another. So the probability of a string a very close game will be the probability of each word multiplied. And since we're dealing with a sparse matrix, remember some frequency will be 0, and to avoid zero probability in our formula, we will use the smoothing method Laplace. Just a small sample correction or pseudo count will be incorporated in every probability estimate, as you can see in the formula on the bottom, where we add alpha to the numerator and denominator. And in this case, we could add alpha equal 1, for example. Another important topic for this week is evaluation. Let's discuss cross-validation and what it means. Cross-validation is a model validation technique for assessing how results of statistical analysis or model will generate to an independent data set. So truly, it is used in settings where the goal is prediction and we want to estimate how accurately a predictive model will perform in practice. So cross-validation will help us to evaluate the quality of the model. It will help us select the model which will perform best on unseen data, and also help us to avoid overfitting and underfitting. Let's review those two important concepts, underfitting and overfitting. Underfitting refers to not capturing enough patterns in the data. And this model typically performs poorly both in the training and the test set, as you can see from the figure on the top right. Overfitting refers to capturing noise and capturing patterns which do not generalize well to unseen data. This model performs extremely well to the training set, but poorly on the test set. And typically different validation strategies exist based on the number of splits in the data set. So we can have a test-train split strategy, where we simply split the data into two sets, train and test set, so that the sample between train and test set do not overlap. And the second one is k-fold validation. We simply average scores after k different holdouts. Every data point gets to be in the validation set exactly once, as you can see from the figure in the bottom, and it gets to be in the training set k minus 1 times. So if our k-fold equal 5, every data point will be in the validation set once, and in training set 4 times. As a general rule, we choose k equal 5 or k equal 10 as these values have been shown empirically to yield test error estimates that suffer neither from excessively high bias or high variance. In our text classification workflow, training and predictions are the 2 main stages involved in building text classifier. In general, dataset is already divided in 2 or 3 splits for training, validation, testing datasets. Notice there's an overlap in text normalization module and a feature extraction module. Each document must go through the same series of transformation, which is preprocessing and normalization, and then specific features pertaining to the documents are extracted. So these processes are always uniform, just to ensure the classification model performs consistently. And we cover some popular feature extraction techniques, and we'll be using some of them. Training the model involves feeding the feature vectors from the documents and the corresponding labels such that algorithm can learn various patterns corresponding to each class and category, and then can reuse this knowledge to predict classes in the future documents. And the combination of these features plus machine learning algorithm, it is our classification model. Often the model needs to be tuned using different model parameters using a process called hyperparameter, just to find a better performing optimal model. The prediction process involves trying to either predict classes or evaluate how predictions are working on new, unseen, or test data. We can evaluate prediction performance of the model by comparing true labels and the predicted labels using a variety of metrics such as accuracy, precision, recall, or F1 score, just to get an idea of how well the model performs. To illustrate how text classification works, let's use the very popular 20 newsgroup dataset, which is available for download directly using scikit-learn. 20 newsgroup dataset comprises around 18,000 newsgroups posts, thus spread across 20 different categories or topics, so we will have a 20-class classification problem. We also need to remove headers and quotation blocks from our text documents to prevent model from overfeeding, or not generalizing due to specific headers. It could be email addresses in those blogs. Scikit-learn has a parameter called remove, where you can indicate what kind of information needs to be stripped out of each file. In our case, we will be removing header, footer, and quotes. We also need to remove empty documents. As a matter of fact, in this dataset, you'll find 515 empty documents. Next, we preprocess and clean our dataset. Refer to the chapter 3, where we cover all necessary preprocessing steps. And now we can add clean corpus to the data frame, and thus we have article, target label, target name, and clean article. Next, we need to build our models on training data and then test and evaluate their performance on test data. So we're going to split our dataset into train and test datasets, and let's use 67% for training data and 33% for test data. And if we check, you'll have about 12K in train corpus and 6,000 in test corpus. Let's start using a basic bag of word method. Of course, you can try next to use TF-IDF or word embedding. We're going to extract features from our train and test datasets. Let's build 2 classifiers and then compare their performance evaluation. And we'll use our bag of word features. This is our first classifier, naive Bayes, which can be imported as multinomial NB. And we also need to import cross-validation scores. We will be checking model accuracy using 5-fold cross-validation to see if the model performs consistently across the validation folds of data. As you notice, we use CV equal 5. When we run our accuracy on test and mean cross-validation accuracy, we get results 0.67 for mean accuracy and test accuracy 0.69. Let's look at regression classifier. We import logistic regression, also apply 5-fold cross-validation, and compare and look at the results with the mean accuracy 0.68 and test accuracy 0.7. Finally, let's look at both classifiers together, and you notice logistic regression slightly outperforms on term frequency score and cross-validation. It is 0.68, and on the test score it's 0.70.